It's time to start Chapter 9, Center of Mass via Integration. Now, we'll take a moment to get into the integration, but one thing you'll notice is we were doing Chapter 15, we're going backwards to do 9. Well, why is that? So, in your previous course, you dealt with doing the center of mass, and why did you need that? Because as you got to rigid bodies, if you're looking at, you would know that the force of gravity effectively acts at the center of mass. So in a rigid body, you're concerned at the center of mass, and it has shape. It's not a particle. Okay, so you had to have some use, as it were, for the center of mass. Okay, so we taught that to you using composite parts was the method that we taught. The problem is that you were just learning calculus and you weren't ready for us to throw a lot of integration at you, so we didn't do that part. So we're now going to go, as we're going to be moving into dealing with rigid bodies for dynamics. So we're just going to finish this story now. Center of mass, and we're going to move towards doing it with integration. So, and after that, we're going to go actually to Chapter 10, and look at mass moment of inertia. Why that's in the static side doesn't, in some sense it doesn't make sense, in another sense it does, and I'll explain when we get to that, but that's the next chapter. So we need to finish the story on center of mass via integration. Okay, so you had a basic equation you were given. So this is a C, so x, the x center of something. This was a weighted average, and you would have done this in your last course where this is for a given I number of parts. For the first part, you would have x1 plus mass of the first part, x2 mass 2 plus x3 mass 3, so on and so forth. But you would have also realized you could have replaced mass, both of these, it could be volume. So volume 1, volume 2, 2, 3, 3. So you could have had the center relative to volume, x1v times v1, x2v times v2, and add all them up. So it's a weighted average. It can give you center of mass, center of volume, center of area, center of weight, whatever you want it to be, for a fixed number of parts. So let's just do one of these problems here, just review using this equation. So here what I have are two blocks. So we have the XY axis. Units are in centimeters. So I have this one block down below that looks like a big 6 by 12 rectangle, except this 3 by 3 right triangle's been cut out. And then this is a 6 by 6 centimeter block right here. So I'm calling this part 1, this is part 2, and I'm going to call this part that was cut out part 3. So in terms of, if I was to express these parts, it's a big rectangle plus this box minus this cutout. Minus means I'm cutting material away. Okay? So if this were all one piece, now I've done this as two separate blocks, but this could be, we could view this as all one big block and then breaking it down like this just to make it easier to handle. So I have three parts. 1, 2, these are additive. Third, takes away. So the way I would normally teach this is that you form a table. Do your part algebra just to kind of wrap your head how you're breaking it down. And so you have three parts, 1, 2, and 3, and I always just put signs if they add material or they take it away. So when you do your average, you remember to put in the positives and the negative signs. All right, so for the first part, where's the center? Well, it's at 6 and plus 3, 6 and 3. I've modeled it as the great big rectangle, so it's 6 by 12 areas 72. I'm going to do a center of area for this because I don't have the depth or I don't have the density of the block. So all I have is the cross-sectional area, so I'll work with that. 2, I've got this block up here, and so if I look in the X, this is 6 across, so the center is at 3, and then it's 6 plus 3 up here, so that's 9. 6 by 6, it adds 36 units of area. Now over here, I've got this right triangle that's been cut out, and the key thing to know in a right triangle is that the center of mass, as it were, in a triangle is a right triangle. Very important, right triangle, got a right angle right here, is 1/3 from the fat end. Okay, so what does that mean? This, if you look along here, this is 3 long. 1/3 is 1. This is the fat end. So, relative to that, I'd have 6 and 3 and 2, so that's 11. That's the X center. Now, 1/3 from the fat end, that means it's 1 from the top. That'd put that at 5. How much area does it have? 3 times 3 times 1/2, 4.5 units. And again, I'm going plus, plus, minus. So the total area here, 72 plus 36 minus 4.5, takes me to there. Okay, then we can just apply this equation we had up on top. And I have both of them for X and Y. So all we do then is we take for each part, we take their X center, multiplied by, in this case, their area. And then we sum the areas here. So I'll take 6 times 72 plus 3 times 36. I'm taking both these columns and going down. This one's negative. So minus 11, the center of this little triangle, times 4.5, its area. Divide by the total area, and we get 4.739, which is somewhere in this vicinity for the X center. The Y center, we simply go this times this, plus this times this, minus that times that, and divide by that, and we get it at 5 centimeters. So that's the classic way you've done this. This should be review, and we'll move on. All right, so we're going to take a look at integration. Here we are. So we have our ubiquitous blob. So we're in XY. That's an ugly Y. Still ugly, but it's better. So we have our ubiquitous blob out in the 3-dimensional space. And here's our little differential mass, weight, volume. That could be a volume in this case. And so what we need to do is add all these differential volumes up, or masses, or whatever they happen to be, and figure out the X, Y, and Z center. This is classically how you did it. There's that equation. This is relative to weight. Okay, you could do it to weight, to mass, to volume, yada, yada, yada. Now, when we go to this blob, and what we're going to do is we're going to have an infinite number of parts. So we're going to have a differential part where its center is at X. All right, so if I take a little, this thing will be at each individual X. I'm going to go to an integral, and I'm going to range over all the possible X's here. And so I'm going to have a differential thing where the center is at X, and I'm just going to run over all the possible X's. And then down the bottom, I'm just going to figure out the weight. Okay? So this equation is the same thing as this equation. All right? I have a differential weight in this case, and its center is located at X. And I'm just letting X take all values. And I'm going to add them all up. And then I'm going to divide by the total weight. Now, this is important here. Notice this differential weight its center is going to have to be located at x. So that's telling us something, though. X is a variable. I'm going to let this range over all possible x's. So that says when I come up with this differential weight or mass or volume or whatever, if this is a variable, it says ultimately I'm going to have to be integrating against x. That variable says when I make this differential weight up, I need a dx, or I'm in trouble. Now, we're going to practice doing that, but let's just kind of take a look at this equation. So if I'm not dealing with Mount Everest, where you might have some variation in gravity over 25,000 or so feet, effectively. For most cases, if you're down at sea level here, we could look at weight is mass times gravity. So I can break this down into g times dm, and the g's cancel, and what we wind up with is the usual case, the center of weight equals the center of mass. Not exactly surprising. So I have xg, the center of gravity, is the center of weight, is the center of mass. All right. Well, if I have mass, well, if this thing has, let's think about this. Here's this blob. If this blob has everywhere the same density, well, then I could break that mass down the following way. Mass is simply density times dV. So I substitute for dm my density times dV. The densities cancel. Sorry, that's a little messy. And then I'm left with the integral x dV over volume. So there's center of volume. Now, suppose further that this volume is composed of some constant third dimension times a differential area. So in one dimension it's constant. Well, then I can break dV down into kdA. The k's cancel. I have a center of area. Or suppose I have a differential volume where I have a constant cross-sectional area. Well, that's this. dV equals this constant area dl, the third dimension. The a's cancel, so I have a center of length. All the same equation as we originally had. It's just we're evaluating it at an infinite number of differential points. Okay? Next time, we'll start putting this to use.